guys, how are you doing? Welcome back to Chemical Kinetics lecture series. In previous class, we had discussed about classification of complex reactions. Later, we have derived an integral equation for the calculation of rate constants of opposing reaction or reversible reaction. Today, we are going to discuss about the parallel reaction. Okay, so now we are going to discuss about the parallel reaction. Parallel reaction. It is also called as the side reaction. Otherwise also called as concurrent reactions. Concurrent reaction. Okay, these are also called as side reactions or concurrent reactions. In complex reactions, if two simple reactions are simultaneously takes place and do not opposes with each other, then they will be called as parallel reactions. For instance, let us take the combination of benzene with chlorine. Combination of benzene with chlorine. So let us take the benzene. We are taking the benzene and combining with the chlorine. So if we combine, there we can get the two types of the products. So in the first case, it is chlorobenzene. Okay, so first case we can get the chlorobenzene. Whereas in the second case, we can get the benzene hexachloride. It is the benzene hexachloride. BHC. Benzene hexachloride. Okay, so benzene hexachloride. So this is the one example, and the second one is take the nitration of phenol. Nitration of phenol. So take the phenol. Phenol is the aromatic alcohol. So it is OH. We are doing the nitration. So add HNO3. So in this case also we can get the two products or two types of the products. So one is, in one case, the first case, we can get the orthonitrophenol. One is orthonitrophenol. Another one is para-nitrophenol. It is OH and it is NO2. One is orthonitrophenol and another one is para-nitrophenol. Okay, so it is ortho product and this is the para product. And the third case is take the action of KOH on alkyl halides. Okay, action of KOH on any alkyl halide. For instance, take ethyl bromide on ethyl bromide. So ethyl bromide formula is, it is CH3CH2Br. So it is combining with the whom? It is reacting with the KOH. Okay, so in the first case, what we can get? We can get the alkene, CH2 double bond CH2 plus we can get the water. And second case, we can get the alcohol, the CH3 CH2 OH plus we can get the KBr. So here also we are getting the two products. Okay, so otherwise fourth one is reaction between benzene disodium chloride and ethyl alcohol. reaction between benzene diazonium chloride, okay, and benzene diazonium chloride and ethyl alcohol, CH2OH, CH3CH2OH, ethyl alcohol. So write the reaction. So take the benzene diazonium chloride, it is N2Cl, plus add the ethyl alcohol, CH3CH2OH, and adding, you can get the two types of products. Okay, so first case what can we get? We can get the ether, OC2H5 plus N2 plus HCl we can get. Whereas in other cases we can get the benzene. So simply write the formula because we don't have the space here. It is C6H6 plus N2 plus HCl plus we can get the acetaldehyde CH3CHO. Okay, so here also we are getting the two types of the products. So therefore what we can say, the chemical reactions which proceeds through the more than one path. See, all the cases we have the two paths, so they are proceeding through more than one path to give the different products. All the cases we got the different products. Okay, we got the different products. Every cases we have the different products, so that's why these were called as parallel reactions. So parallel reaction means, okay, we define the chemical reactions which proceeds through more than one path to give different products are called as parallel reactions or side reactions or concurrent reactions. Okay, side reactions or concurrent reactions. In parallel reactions, the reaction which utilizes the major portion of the reactant is called as major reaction or main reaction, whereas other is called as side reaction. So that's why if you take the first reaction, okay, so in this case this is the main product or major reaction. Main product, the product is the main product and it is the major reaction, whereas this is the side product because it is side reaction. It is a side reaction. It is the main reaction. So in the nitration of the phenol, orthonitrophenol is the major product. It is the major product. Hence this is the main reaction. And this is the side reaction. So it is the minor product or minor reaction or side reaction. Okay, and reaction of KOH. Okay, so it's depending upon the type of the KOH. In one cases we should take the aqueous KOH, whereas other cases we should take the alcoholic KOH. So if you take the alcoholic KOH, we can get the alkene, whereas if you take the aqueous KOH, you can get the alcohol. Okay, so one is major, other one is the minor, depending upon the type of the KOH. And in other cases, so there also it is depending upon the condition. Okay, so that's why in parallel reactions, okay, we can be able to convert the side reaction into the main reaction by adjusting the experimental conditions. Okay, so both the way we can do it. Okay, so in one cases, by adopting the suitable condition, the main reaction is converted into the side reaction, whereas other cases the side reaction also converting into the main reaction. So this kind of the feasibility we have in the parallel reactions. Okay, yes. So again, if you take the important characteristics. So take the important characteristics of the side reactions. So if you take the important characteristics, so there first one is what we can say. So check the reactions. Here we have the two These are nothing but the simple reactions only. So two simple reactions are taking place simultaneously, and both are do not opposing. Okay, so they are parallelly taking place. Okay, so that's why they are the parallel reactions. Okay, so that's why what we can say first one is simple reactions takes place simultaneously but do not opposes with each other. Okay, so takes place simultaneously and do not oppose that is the first important characteristic of the parallel reactions. Okay, second one is the products are independent. Okay, so these products are independent, that means they don't have any chemical affinity. Okay, so the products do not have chemical affinity. Okay, they do not have the chemical affinity, that's why they are calling them as the independent products. Okay, so products do not have, otherwise what we can say, products are independent. Products are independent, otherwise they don't have any chemical affinity. So that is the second characteristic. And the third one is if we plot a graph between the concentration and time, it is seen that the concentration of the reactant is gradually decreases, whereas products are gradually increases like other reactions. Okay, so now we have to plot the graph between the concentration and time. Okay, so take time on the x-axis and concentration on the y-axis. C means concentration, T means time. So first case is the concentration of the reactants decreases gradually, whereas if you take the product concentration, it is increases. Here we have the two products, one is the major and another one is the minor. So both the cases it is increases. So it is the major product, and it is the minor product. Okay, so this is about the which one? Plot between the concentration and time. Okay, you can get the graph like that. So these three are the important characteristics of the parallel reactions or side reactions or concurrent reactions. Now we have to take the reaction kinetics. So let us take the reaction kinetics. If you take the reaction kinetics, so here also we have the two conditions in first cases when both the reactions are of same order, whereas in the second cases both the reactions are of different order. Okay, so now we should take the first condition. So that is when both the reactions are of same order. Both the reactions are of same order. Okay, so that is the first condition. That means here side reaction and main reaction both have the same order. Okay, so that is the first condition. So anyway, in order to derive the rate equation, we should assume the main reaction and side reaction both are follows the first order kinetics. Okay, both are following the first order kinetics. Okay, so both are following the first order kinetics. Then let us consider the reaction A. So this is A. A is giving the B as well as C. Okay, so here we have the K1. So it is the K2 and this is the K. Okay, so it is the parallel reaction or side reaction or concurrent reaction. Okay, concurrent reaction. Okay, so here K1 is the first order rate constant. Okay, and K2 is also first order rate constant of side reaction. Okay, so when we have assumed as a side reaction, if if K1 is greater than K2, then what happens? A gives B. Okay, A gives B. This is the main reaction. Main reaction. Okay, A gives B. That is the main reaction. Whereas A gives C. It is the side reaction. That is the side reaction. Okay, so this is the K1 and this is K2. Okay, so this is the side reaction. Okay, so if it is so, and later just you should assume A concentration is small a. Okay, the initial concentration of reactant A is small a, and after time t, X moles per liter of A will be transforming into the B and C. Okay, X moles per liter of the A is transforming into the which one? B and C. Okay, so then after time t, the concentration of reactant A is A minus X, whereas the concentration of B and C are XX respectively, otherwise simply X. Okay, so simply it is X. So that's why how can we write? How can we write that? So take three things. So one is A, another one is B and C. So initial concentration, initial concentration of A is, it is small a, whereas initial concentration of B and C are 0. Okay, they are 0. So later after time t, so what I told you, X moles per liter of A is transforming into the B and C. So then the net concentration is A minus X moles per liter, whereas this is X moles per liter and X moles per liter. Okay, so X moles per liter. So this is about the concentration of the reactant A, B, C after time t. Okay, after time t. So now we should take the rate of dissociation of the A. Okay, so the rate of dissociation of A is written as minus dA by dt is equal to the rate of formation of B dB by dt, which is equal to dC by dt. Okay, dC by dt. So whereas otherwise in other words minus dA by dt is equal to K into A minus X. So here K is equal to overall rate constant, overall or net rate constant, overall rate constant or net rate constant, and yes, if you take the rate of formation of B and C, how can we write? So let me see how we can write. So the rate of formation of B, okay, the rate of formation of B, B is equal to, how can we write? dB by dt is equal to, it is K1 into A minus X, because both are forming from the A only. Okay, and next one is the rate of formation of C. The rate of formation of C is equal to, it is simply written as dC by dt is equal to K2 into A minus X. Okay. So K2 into A minus X, both are forming from the A reactant only. So that's why we are equalizing. Okay. So later, if you want to calculate the net rate of the reaction, we need to add the both the reactions. Which one? The rate of formation of B as well as the rate of formation of C. So both we have to add up. So if we add up, the net rate of the reaction is equal to the net rate of reaction, dx by dt is equal to which one? The rate of formation of B, dB by dt plus dC by dt, dB by dt plus dC by dt. So if we substitute their values, so that becomes very simple equation. So now we have to simplify it because we need to calculate the rate constant of parallel reaction. So we need a simple equation. So that's why dx by dt is equal to, so dB by dt is equal to, it is k1 to a minus x. So k1 into a minus x. Okay, k1 into a minus x plus dc by dt is equal to k2 into a minus x. K2 into a minus x. Now again you need to simplify it. So if we simplify, so how can we simplify? Just take the k as the common factor. So if you take it, yeah, it is not the k, so we should take the a minus x as the common factor. So if you take a minus x as the common factor, it is k1 plus k2 into a minus x. Okay, k1 plus k2 into a minus x. And it is again replaced by the k. So k is the overall rate constant. Okay, k into a minus x. So where k is equal to net rate constant. Net rate constant. So therefore overall it is dx by dt is equal to k into a minus x. K into a minus x. Now you just send the a minus x to the left side. So if you send a minus x to the left side, dx by a minus x, dx by a minus x is equal to k into dt. Now you should integrate the equation. On integrating both sides, on integrating both sides. So what does it become? Just you should take the integral equations. So integration of 1 by a minus x into dx is equal to k into integration of dt. So integration of 1 by x dx is equal to minus ln x. So in that way, if you want to simplify this equation, so it becomes as minus ln a minus x is equal to kt plus I. I is the integral constant. So you assume this is the equation 1. Okay, equation 1, it is the equation 1. Otherwise, instead of 1, just you assume it is the 2, and this is the equation 1. Yeah, this is the equation 1. Okay, it is the equation 1. Okay, so here I is equal to integral constant. I is equal to integral constant. So again, if t is equal to 0, then x is equal to also 0. Okay, if we didn't started the reaction, then no transformation. Okay, we have the only pure reactant. That's why x is equal to 0. So therefore, in that condition, minus ln a minus 0 is equal to k into 0 plus I. So minus ln a is equal to I. This is equation 3. Equation 3. Now from equation 2 and 3, how can we simplify it? So here simply from equation 2 and 3 minus ln a minus x is equal to kt minus ln a. Now you bring the ln a to the left side. Now it becomes ln a minus x plus ln a is equal to kt. So how can we simplify this further? So simply it is how was it? It is log a minus log b. So log a by log b. Okay, log a minus log b is equal to log a by b. So in that way, it is ln a by a minus x. A by a minus x is equal to kt. Okay, kt. So otherwise, if you want to further simplify it, then kt is equal to 2.303 log a by a minus x. Log a by a minus x. Okay, so this is the final equation. So this equation is used to calculate the rate constant of parallel reaction. So here k is the overall rate constant or net rate constant. Okay, so this is about the derivation of integral equation for the parallel reactions. So next one is derivation of half-life. Okay, it's calculation of the half-life. Half-life. So half-life means how can we define the minimum time required to become insert concentration into the half. Okay, the time which is required to become half of the initial concentration is called as half life. Okay, so for first order reaction, T half or T.5 is equal to 0.0693 by K. Okay, so here we have the K1 as well as the K2. So that's why K1 is equal to 0.693 by T of 1 and K2 is equal to 0.693 by T of 2. Okay, so if you want to calculate the K1 plus K2, how can we calculate? So K is equal to K1 plus K2. So therefore K is equal to K is equal to 0.693 by T of 1 plus 0.693 by T of 2. So if we simplify further, K is equal to 0.693 into 1 by T of 1 plus 1 by T of 2. Okay, 1 by T of 1 plus 1 by T of 2. So further if you want to simplify it, so K is equal to 0.693 into or by okay, otherwise into 1 by T of 1 by T of assume it is net, T of net. Okay, so T of net. So this is about the calculation of half-life of the parallel reaction. So N is equal to overall T of or net T of net. can stop here. Tomorrow we will continue.